So we just saw that money can grow exponentially under compound interest. And it would also do the same thing with continuous interest, since the formula for continuous interest is also an exponential function. But many other phenomena in life follow an exponential growth pattern, provided that we take out some, natural processes. For example, bacterial growth. All right, if bacteria was allowed to just grow, without bound, bacteria would grow exponentially. All right, and so if you counted the amount of bacteria over time and you plotted, those numbers, you would see an exponential function graph. Now that's under the assumption that real life doesn't happen. All right, in the case of bacterial growth, say, in an infection, somebody gets an infection. Obviously, there are some interventions that take place, antibiotics, for instance, and so obviously that would stop the bacteria from growing and hopefully gets out of your system. But we're kind of throwing all that real life stuff out, real life interventions, I should say, and in doing so, you get what's called the law of uninhibited growth. And it's a two-way street, though. Things can depreciate over time, in which case they would follow an exponential pattern as well. For example, population. Okay, population growth. Population tends to grow exponentially, but of course we could have a population decay. Maybe there's an outflux of people, moving from Michigan, over to wherever, Arizona or something like that. Radioactive decay, so things break down over time. And if you were to plot how much of the substance is left as each year goes by, you would find that the graph would be an exponential function graph. Depreciation of a car's value, the number of hits a website experiences, that tends to follow an exponential format. Cell division does, which, guys, I got to blow your mind for a second here. Did you know that cells multiply by dividing? That's crazy, isn't it? Another example is what we saw just a few minutes ago, continuous interest. So if we don't allow any real life interventions or restrictions, these follow what's called uninhibited growth or uninhibited decay. And there's a particular formula that we can use to model all these scenarios, and that's referred to as the exponential law. And I'm going to go ahead and provide that formula to y'all. It goes A of t, so that's function notation, equals A sub 0, not the Mortal Kombat character, by the way, times E, and in the exponent, k times t. And I want to note that this is very similar to the formula for continuous interest. The only differences are what we're naming the initial value and what we're naming as the rate. Okay, instead of P, we have A sub 0, which that stands for the initial amount. We still had the base E, and in the power we have K instead of R. And what K refers to is the growth or decay rate. So if it's exponential growth, it would be the growth rate. If it's exponential decay, it would be the decay rate. And one really cool thing about the exponential law is that time, t, can be in any unit. It doesn't have to be strictly in years like the continuous interest formula has to be. So what we're going to do for our first example is pick apart a specific exponential law formula. It says here the size A of a certain insect population at time t, which is in days, obeys the function a of t, so the amount as a function of time, equals 400 times e to the 0.06 t. Anybody recognize that artwork over there? It's from my all-time favorite rock band, Alice in Chains. It's from their album Jar of Flies. In part A, it says determine the initial amount of insects. If you look at the formula they give us, 400, yep, no excuses was on that one, you got it. 400 would represent that value of c that we had when we were defining what an exponential function is at first, c times a to the power of x. And I mentioned that c stood for the initial value, and that doesn't change with the law of uninhibited growth. Whatever number is in front of e, that's going to be your initial amount. So the initial amount of insects is going to be 400. What is the growth rate of the insect population? The growth rate is given by the value of k. Can anybody identify what our value of k is in this function? Yep, 0.06. We could express that as a percent, 6% in fact, and what this means is that the population grows by 6% each passing day. So on day 2, you would take 400 and increase it by 6%. Then on day 3, you would increase what you just got by 6%, and so on and so forth. Part C, what is the insect population after 10 days? 10 days is a particular value of t. And so to figure this out, we would have to take 10 and plug it into our function that they provide us with. All right, you guys want to crank that out and type in the chat, maybe round to the nearest bug. What do you think about 729? So 729 insects. So a little fun fact about the Jar of Flies album is that I think it's the only EP to like go #1 on the Billboard charts or whatever. And they recorded that album in 1 week. I think they had something happen where the band had to like move into like this warehouse or recording studio, and I think they were just like extremely bored, and so they started to just write songs and they put it all together in just 1 week. And the bass player for this album, who's the current bass player still, Mike Inez, he was recruited from Ozzy Osbourne, and their original bass player they had to kick out of the band because of a drug addiction. And so, they were looking for a bass player, and Ozzy Osbourne caught wind of it and said, "Hey, I got this really good bass player. Why don't you guys give him a try?" And so this is the album where he was first featured on it. Fun fact. Oh yeah, they're great, just great. All right, let's look at our next example. The formula A of t. I agree, Robert, for sure. It's 165 times e to the 0.039t. This models the population of a particular city in thousands. So when you see 165, you can assume that that's 165,000. And this is t years after 1998. How long will it take the population of the city to double? Okay, so big money question is how long. So we're to assume we don't know a value of t. We need the population to double. The initial population is given by 165, which is a shorthand version of 165,000 based on the description. If we need the population of the city to double, then what that means is A of t needs to be 2 times 165. Okay, so if we double 165, we're looking at 330. So essentially, we need the population to go from 165,000 to 330,000, and we got to figure out how much time is needed in order for that to happen. And then once we figure out that time, we can add it to 1998 to figure out what year that happens in. So on the left, let's write 165 e to the 0.039t. And as you can see, we have an exponential equation to solve. And that's due to the fact that t is in the exponent. So I'm going to give you a minute or so to see if you can solve for t. If you need help with that, you can look at the last example in section 6.7. The solution is very similar to it. And once you get the answer, if you want to pop it in the chat, I'd greatly appreciate it. Yep, you're right on the money there, Isabel. Let's isolate the exponential expression by dividing each side by 165. E to the 0.039t equals 2. By virtue of the BS method, we're going to get 0.039t equals the natural log of 2. And then you can divide each side by 0.039. And this comes out to about 17.77 years. which I'm going to round that even further to 18 years, because that'll make it a little bit easier to figure out in what year that this happens in. What could we do to figure out what year this happens in? We could take 1998. Yep, add 18, and we get 2016. Okay, so in 2016, according to the law of uninhibited growth, the city will have doubled since 1998, the population of the city. All right, again, law of uninhibited growth means no real life factors such as people leaving the city, effects in birth rates and things like that. So when we do account for those things, it requires a different type of function that's quite different from the law of uninhibited growth. But we won't be taking care of that in this course. What we will take care of, though, is this last example. So the population of a Midwestern city follows the exponential law. Okay, so when you see that, just quickly jot down the formula for the exponential law. It says if the population decreased from 900,000 to 800,000 from the year 2003 to 2005, find the decay rate. Now, first of all, it's a decay rate because it's talking about the population decreasing, and the decay rate is given by k. So this is what we're trying to find in this problem. So that means we should be able to come up with values for a of t, a sub 0, and t. Now it says here that it decreases from 900,000. That means this would be the initial amount. And then the final amount is given by 800,000. That would be a value for a of t. And this happens between the years 2003 and 2005. So what would that mean for our value of t? T is 2. Yep. So let's go ahead and plug all this information into our formula. 800,000 on the left equals 900,000 on the right times e to the power of k times 2. All right, I'm going to send you off on another mission to solve for k this time. I'll check in with you in just a couple minutes to go over the solution, and then we'll take a break. All right, you ready? Let's go ahead and isolate the exponential expression. We can divide each side by 900,000. On the left, I'd actually like to leave that as 8 over 9, which is what that fraction reduces to. Then on the right, I'm going to write it out as e to the power of 2k. And then by virtue of the BS method, we'll have the natural log of 8/9 equaling 2k. And then we can divide each side by 2 to get k is equal to the natural log of 8/9 all over 2. And yep, I would recommend punching this into the calculator and rounding, perhaps to 2 decimal places. I got negative 0.06. Or if we want to go to 3 decimal places, looks like Isabel has 3 decimal places. And quite honestly, I know our default rounding instructions are 2 decimal places, and there aren't any rounding instructions here. But when it comes to these exponential models, the more decimal places that you round to, you know, the further out that you round, the better. So, you know, I'm suspecting, you know, for things like this, at least 3 decimal places, maybe 4 decimal places in real life. All right, so maybe I'll go to 3 decimal places. So negative 0.059. That would be our decay rate. And we could actually express this as a percent, minus 5.9%, which means that the population is decreasing by 6% each year.